Okay. In this talk, we are going to see some basic concepts of deep learning, and then we are going to see an ePython notebook with a quick pipeline to build your own convolutional neural net, so we can classify the Star Wars ships. Afterwards, if you want to grab and make some videos, you can do it, and you can build your own classifier. So I'm a PhD student in computer science back in a Patagonian research lab. I'm already submitted the thesis, so I have to go back to defend it, finger crossed. I'm a member of the image science lab back in Bahia Blanca. I'm a professor at the engineering department back in the Patagonia University. I'm a really happy member of Linux Chicks Argentina. I'm the co-organizer of SciPy Latin America, the first two, and I just give a hand in the next ones. So let's start with the basic. In machine learning, we have supervised and unsupervised learning. So we're going to work with the first one. So for the first one, we want to infer a function with labeled data. So that labeled data means that we have our data set has each row has a value with attributes. For example, an image, you have a bunch of pixels, and you have a label type that says, for example, it's a car, a house, or something like that. So when you have labeled data, and you are inferring a function, when you're training, you can have, by the end, an objective function to measure the error. So you have your predicted value, and you have the real value, and you can compare how far are you from that. So in the next chain, in the next step, you can change some parameters and get closer to a lower error. So first, we're going to see a little bit about neural nets. So we have the basic perceptron here. We have an input layer, hidden layers, and an output layer. So in the input, we're going to have the feature values, for example, a pixel on an image. The hidden layers is going to create the nonlinear functionality there. And the output, you're going to have one node for each type of class you want to classify. And in each node, you're going to have a score. Hopefully, the highest score is the correct class of the input values. So when you want to get a value from your neural net, you're going to do a forward propagation. So something I didn't say, that you have the weights initially are randomized, initialized. So probably the first time you run the net is going to be like really bad results because it's totally random numbers. So when you want to get a value, you do forward propagation. From the input, you go to each node. You have a weighted sum that is in the B section. That sum goes to an activation function. There is a mapping function that takes one value, applies a function, and returns to another space. For example, that ReLU, all negative values goes to 0, and the other one linears. So that is going to be the input for the next layers that we're going to have. So the thing is that when you get to the output layer, you can measure the error. You have labeled data, so you can see an error between the actual value and the predicted value. That function error, it's named an objective function, and we can see an example, a graphical one in the C part, that all the possible values of that function. So we're always going to try to search the lowest part of that function because that means the lower error we can get. And that's the lower difference between the real value and the predicted one. For that, we use algorithms of gradient descent algorithms to search for the slope and the place that we have to go to get the lower one. One of the main problems of these algorithms is local minimum. So you are running with your step and your vector through a surface, like a terrain, and maybe you get stuck because you say, okay, this is the lower I'm going to get, so maybe I should just converge. But the optimal is go to the global minimum, so that's the lowest error possible that you are going to get with your data. So what changed? So neural nets are from the 90s, so there is nothing new there. But the thing is that we have a much more amount of data available, and we have GPUs, graphical cards, that let us program these optimization functions to run really quickly over huge architectures of neural nets and datasets. So we have in deep learning another interesting thing is you start with raw data. So if there is someone from computer vision, we usually do this pipeline. When we get the raw image, then we do some engineering feature extraction. This is a handmade pipeline. And when you use some threshold or some edge canny searching or some stuff to extract the features, and then you pass that to a model to classify. So deep learning takes that step for you. First, it's going to do some extraction of representation of information. And when when the extraction features occurs, pass automatically that to the perceptron, the common layer, that does the classification. Some examples, for example, in CT scans for segmentation, for tumor, for example. At the end of the presentation, I have all the papers where these examples come from. Ubisoft uses for human-like movements on different types of terrain. So if it's running or crawling down a tube, something like that, you have automatically human-like interaction with the individual and the terrain. A really fun one is Dance Dance ConvNet. Do you hear about the game that you have to, press some arrows and do the dancing? Okay, they take the audio of the music and they have the choreography. So they train a net, so you can give him a new theme of music and it generates a new, really nice choreography. Other examples for Tesla driving, you have this pixel-wise segmentation that you have information if something is the road or is a sidewalk or stuff like that. You have really better compression methods with deep learning. And another case is if you want to do landmarking, you can use your net as a regressor, not a classification, and you can locate some specific points in an image. So in deep learning, you have a huge variety of different architectures. You have LSTM networks for, I'm mostly seeing text processing. You have recurrent neural nets. In this case, we're only going to see ConvNets, so please don't think that deep learning is equal to ConvNets. They work really good in computer vision area. So this type of architecture, you have two stages. You have the first one that does the feature extraction part, and the second one that does the classification. So in the feature extraction part, you are going to have two types of layers. You are going to have the convolutional layer that is going to subtract features, and you're going to have a max pooling layer that is going to take only the important ones. So you are going to repeat this type of convolution max pooling several times to get several levels of feature abstraction. So for example, the first layer, you are going to have like edges, corners, very simple features. Then you're going to go to a little bit more inside the net. You're going to have texture, and then you're going to start taking part of the objects that you want to classify. When you have this high level of features, then you can pass to the classical perceptron network that is going to classify with those features. So let's see first the convolutional layers. So imagine that the orange part is the input or the image that you're working with. The lighter orange is a kernel, and it's going to do a dot product over that part of the image. So that dot product is going to give you one value that is in the red matrix, and you are going to pass this kernel over all the input image. and you're going to have this convol feature. So the way that you move this kernel is called a slide. You can define from Python how do you want to slide your kernel. You can define how many kernels do you want, and their size. For example, that one is 3 times 3. And you can use zero padding. If you want to take information in the borders of the image, you want to fill up with zeros around the image to get more information. So there is a really nice guide called Convolutional Arithmetic for Deep Learning. It's done in Ciano. It's really nice. You have a bunch of examples you can take off. So the second layer that we talked about was max pooling. So this is, imagine that's your convol feature, and you're going to take like a window, and in that window, you're going to take the max values of that information. So for example, this is a 2 times 2 window. You're going to, for the first and the left up, you're going to take 6, then 8, 3, and 4. And that's the feature that you want. That's the one is going to pass to the next layer. Because one thing we didn't talk about yet is that these big networks, and sometimes if the data set is small, they are going to overfit. Overfit is when the networks memorize all the examples and doesn't extract any discriminant information, really. It's just memorizing all the, if there is an image, it's memorizing all the pixels. It's not taking any important pixel at all. Has the capacity so it can memorize all the information. So when you gather new images, it's not going to work. It's not going to generalize well because just memorize didn't learn any important features. So to battle this, we have regulation methods. In particular, dropout is quite easy for implement and really effective. You can add a probability to the node to disappear. So in each running, you can ask, okay, you stay or you're going. So when you train your network, it has different structures every time you are training it. So in that, so you don't get the node used to have the same neighbors all the time, to have the same weights, and to have the same outputs. That's a way that you can, doesn't matter how the local neighbors' values are, so it's still going to have good results. So till now, we only see the building blocks that we are going to use for the network, but we can have a sort of pipeline or debugging stage of how the network is doing. So the first thing is that you have to split your data. You want the most of your data going to training, but you want a little bit to do validation, to do this hyperparameter tuning, and you want, like in this example, 30% of your data to go to testing. This is really important. So the network during training never have to see the test elements, because you want to see if the network really learned something or it was just memorizing all the elements in the training set. So for debugging the network that is already trained, you have these two graphs that are like really helpful. For example, the first one, you have the error measurement, and in the x-axis you have the epoch. One epoch is when the network sees one time all the data set and updates and changes the parameters itself. That's one. So the first one probably is going to be a really bad accuracy, and you hope that it's going to be better each time it sees the data. So if you remember when we talk about gradient descent algorithms, we have a learning rate, we have a value that says how much we can change our parameters. That how much can be set up from Python, and you can use this graph to check out if the value that you gave was too high, too low, or it was correct. So if it's too low, you're going to have these linear curves. So you're going to take much more epochs to get a lower value, and you're going to use much more computation, and you're going to lose more time to get that value. So probably you should turn up a little bit. So if you are in the high curve That means that you did a learning rate too high, you're taking steps too long, and you get stuck in a local minima. So it's going to stay there, and it's not be able to get a little lower error. So the nice one is that you're going to have in the same amount of epochs, you're going to have a lower error. So that's a way that you can debug if your network is well trained or you should change some parameters. And about overfitting, so you have the training set performance and you have the validation set, that 10% that we saw that we split in the beginning. So if the performance of the training set goes like really up and you say, no, I'm amazing on this, I'm like 99% all the time, but my validation curve doesn't do the same score, so that's probably overfitting. If the validation set drops down, it's like I'm not getting any better, even worse, and it's just memorizing all the training elements that I give it to the net. So a nice thing to do is just drop out these removing parts of the node, or for example, early stopping. So you set a sort of patience in the network, and you say, okay, if after 100 iterations, my loss didn't change, I can stop right here. Otherwise, I'm just learning all my elements. So for doing this convolutional neural net, we are going to use OpenCV just a little bit to open the images and process some basic stuff. From scikit-learn, we are going to use the metrics module and the cross-validation to split the data and check some metrics. And Pandas and Numpy for getting ready the data for the network, and Lasagne to build it. So the setup, you can use it via pipstall, or you can use Pablo make a wonderful Docker image. You can send them a +1 in Docker Hub. NVIDIA that has a Docker NVIDIA. 5 minutes left. Oh, come on. You can use Docker NVIDIA so you can run your image and has access to your GPU. So that's really cool for training. So let's go to the demo. So F1. So we want to classify these 3 ships. We have the Millennium Falcon, a K-wing, and a Lambda shuttle. Our image is going to look like this. Mostly our videos, and we just chomp the frames off of it. We are going to use grayscale basis. We only have 1 information per pixel. And the size of the images are really slow, 128 times 128, because I want to put all the images back in my CPU, and I only have 2 gigabytes of RAM. So we are going to use Pandas to load the images. I already ran everything because I was thinking that this might happen. So you have the image information right here, is a grayscale value, and you have the model. With Pandas, we can use something called factorize, so we can see 0 for for a Falcon, 1 for a K-wing, and 2 for a Lambda shuttle. So this is information that the network can understand and not the strings. So we are going to load the data. For that, we need to normalize between 0 and 1, because all our conversions methods converge to 0. So when we are tweaking the network, it's going to stop in 0. So if we start with 125, imagine what it took that long. So we normalize in this way. We have to tell the type of data that we are going to use, because this is going to a GPU, and it doesn't understand Python yet. And the Y is going to be int 0, 1, or 2 that the classes of the network are. Then we can import all the type of layers we talked before, and we can build it in this way, like a Python list. So you have your input layer with the shape is 1, 128, 128. If you use RGB data, this will be 3. And we have several repetitions of this construction of the convolutional layer plus the maximum layer. Several times to get several levels of abstractions, and then you have the classic perceptron and the output with 3 nodes because we only have 3 classes of chips. Then we can create the net with the layers we define, the update method that we are going to use to change the parameters inside the network, and the amount of epochs I'm going to use for that network. So those are the parameters you can change. This is a really nice paper if you want to see how to set up your network. So here we use cross-validation to do the train test split. You say, I want the 30% of my data to test. So we are going to train our network with 3,000 images. So we have this method called fit. Then we can see the first epoch, the accuracy is pretty bad because it's random mostly. But each time you see again and you update again your weights, you get better and better accuracy. If this is not happening, you just Ctrl-C and change the network structure. So this is already trained. So I have a snapshot of the network with the best weights possible. We can see some metrics from scikit-learn. This is for the class 0, 1, and 2, and this is the amount of elements that you use to calculate that metric. We can see our curve and see maybe it's quite linear, maybe I can little bit higher my learning rate. We can see the confusion matrix. So here you can see if the network is mistaking some of the classes with another ones. So you are always going to hope that this is the darker part, the diagonal, because if you have some color here, it means that a falcon ship was mistaken with a cow wing. So do I have to train my network every time I want to use it? No, you can use a pickle. You can save the screenshot of your best network into a pickle, and then you can just load it again and use it to predict things. You can check information. You can take just one image and use the function predict to ask for the type of the ship that it is. You can ask how sure is the network that that's the class corresponding to that with predict probability. You can ask with this plot occlusion, you can see which part of the images are important for the net to classify that as that image. That's a little bit of introspection of the network. You can see the final weight. This is the value that you were training so hard and so many times. You can see how they activate, how each kernel looks in the input of the image, like this one, for example. And then we are going to see this classification over video, so some sort of real-time classification for that. So you can see here, each frame is sent to the network, predict, and then go back. So you have a few times was mistaken with the other one, hopefully with lower probability. And I leave you some links if you want to go deeper on this. And just this, and this is my final. So after you build your networks, you say, okay, what more can you do with these things? Well, for example, one thing is it's really tricky to get the correct architecture and learning rates, a bunch of parameters. So there is a lot of people working with reinforcement learning to create automatically the best performant networks. So it's like a meta learning over there. So you have a bunch of research going to introspection to see what's happening inside the neural net and how it makes these decisions. a really nice paper, opening the black box of deep learning with information theory. Is really nice paper. And the other thing is that we are into a point that we have a lot of data, but nothing is checked. And it's labeled data, and humans are biased, so the labeled data that we handle to the network is biased. So that's a bunch of things to look for. There are other libraries, PyTorch, TensorFlow, and Keras. PyTorch has an amazing gallery and documentation, really recommend it. And that's it. You can find all the code there. Sorry if I was too long. Okay.
Well, that's great. Thank you very much. So I think when it comes to questions, are you going to be about for the...
Yeah.
Okay. Are you happy to take questions from people to come up and ask? Yeah. Okay.
Yeah, no
all right.
problem.
Well, thanks very much, Celia, and also we'll wish you all the best.